Okay, I know that's all really wishy-washy, so let's jump in and actually get some data to play with. We only have one regression this week. You might notice I've got a second set of syntax down here with the beta term. When we get to that, I'll talk about it a little bit more. There's my output. There it is. Okay, so what we can see is that we have an ANOVA model, and if you compare it to last week's, you'll notice that now we have 3 degrees of freedom here, whereas last week we had 1. Don't worry too much about this. We're doing ANOVA next week, and then this table will begin to make a bit more sense. We can see that we have 24 observations, and our F is 8.62. We can see that this is significant. So the fact that this is significant tells me that at least one of my predictors must also be significant. My R-squared is 0.56, so that's telling me that 56.4% of the reasons why a person got the rating that they did on their project can be explained due to the number of hours put in for research, the number of hours put in for building, and the level of innovation of the model. Okay, so let's go down, now that we've looked at this, let's go down and look at our actual regression statistics. We can see that we have all 3 IVs as well as our constant. Our constant is -14, and here what our constant's coefficient represents is the expected ratings that a person would get if they had 0 research hours, 0 building hours, and 0 innovativeness. So if they had 0 on all the IVs, what would the mean rating be? And in this case, it's -14. So we spoke last week about the fact that this doesn't really make sense to have a -14, but for the mathematics of determining the significance of the regression, perfectly fine. And like last week, we're going to ignore all of these other constant statistics. We're just interested in the coefficient. Now, very quickly, if we look at research, we can see that for every 1 unit increase in research hours, or an hour spent doing research, the rating goes up by 3.45 units, and this is controlling for the number of hours spent building and the level of innovativeness. So regardless of how many hours you spend building, regardless of how innovative your project is, you're going to get an additional 3.44 points of rating for every extra hour of research you do. That has a standard error of 1.85, a t-statistic of 1.87, and a p-value that's above 0.05, so we actually have a non-significant result. And if we look at our confidence intervals, we see we have a negative and a positive, so 0 is in this confidence interval, so it does make sense that this is non-significant. Now, interestingly, my t-statistic here of 1.87, if I square it, I won't get 8.62. We can do this. 1.87, and I square it, and I get 3.49. So the reason for this is this research effect is only the unique effect of research, whereas this F up here is the combined effect of all 3 predictors together. So you can't actually separate out this F into these 3 T's. You can't do it. It doesn't work like that. This worked well last time when we were looking at simple linear regression, but it does not work at all for multiple. Okay, if we look at build, we can see build has a coefficient of 0.17. So for every 1 hour extra of building time that you have, your ratings increase by 0.17 units. It's not very much at all, and that's controlling for the number of hours spent doing research and the level of innovativeness of the model. That has a small standard error, a t less than 1, and it's non-significant. And again, we can see 0 in the confidence interval here. Finally, we get to innovativeness. It has a coefficient of 6.7, so 6.696 rounds to 6.70. So that's quite decent. For every 1 unit increase in innovativeness, your ratings will increase by 6.70 units. So that's considerable. And it has a standard error of 1.9. It has a very large t compared to the others, 3.5, and is significant. And here, when we look at the confidence intervals, we can see they're both positive. So what this is telling me is that controlling for research and building, innovativeness is actually a significant predictor of ratings, but the same can't be said for research and building. So really, it appears that innovativeness is the only unique predictor of ratings. Another way of saying this, I guess, is if I could only put my money into one of these three things, I would put it into innovativeness. Now, what you might find is that really in this data, for people to have high levels of innovativeness, they probably needed high levels of research and building. But it wasn't the hours of research and building that actually got them the ratings, it was the innovativeness. So what this could mean is that the fact that we had a significant effect for research before could simply be a byproduct of the fact that research could translate to innovativeness in some way. And you got that overlap in variance. Okay, now following this, there is another approach that I mentioned, another thing that we can do. And I will come back to the regression equation in a minute. I haven't forgotten that, we will come back. I can use the beta subcommand. Now what the beta subcommand is going to do is it gets standardized betas. So effectively what this means is that all of my betas will be on the same scale. So at the moment how our betas are described is they are a 1 unit increase in the IV. How much does that change the DV? So for innovativeness we saw that you got 6.7 units increase in the DV for every 1 unit increase in the IV, every 1 unit increase in innovativeness. But if your IVs are on different scales, then a 1 unit increase means something very different from scale to scale. So for example, a 1 unit increase on a 100-point scale only represents a 1% increase on that scale. So then your beta is how much does the DV change for a 1% increase in your IV. Yet if I had a 4-point scale, then a 1 unit increase represents a 25% unit increase. And so then my beta represents how much does the DV change for a 25% increase rather than a 1% increase. And so if I wanted to compare my 4-point scale to my 100-point scale, it's really hard to say, well, 1 for 1, which one's better? So if you use standardized betas, effectively what you end up doing is you put everything onto a z-score, and that z-score can then be used to directly compare everything. Everything we've put on a mean of 0, standard deviation of 1. So let's have a look at this and see what comes out. Now what you will notice is that all of the statistics here and up here are exactly the same. The only thing that's changing is over here. And we lose our confidence intervals. So up here we can see we had confidence intervals. Down here we get beta instead of coefficient. Now technically they're both betas. These are standardized betas. These were our unstandardized betas. And now what we can do is we can directly compare them, and we can say, well, for a 1 standardized unit increase in research, we get a 0.31 standardized unit increase in ratings. For a 1 standardized unit increase in building, we get a 0.11 standardized unit increase in ratings. And for a 1 standardized unit increase in innovativeness, we get a 0.54 standardized unit increase in ratings. So what this is telling me is of these 3 different predictors, innovativeness has the largest effect, 1 for 1 compared to the others. This is followed by research, and then building. So it's really good practice when you do have multiple regression to get both your confidence intervals, but also your standardized betas. Because your confidence intervals help you to interpret the data and go, well, how much variation is there around my coefficient? But your betas also give you an indication of, well, if I make everything equal, what has the biggest effect? Now, as promised, let's talk about the regression equation. So last week, the regression equation was simply the expected DV score, so EY, equals our alpha plus beta 1. All that's happening now is we're going to go plus beta 2 plus beta 3. It's the same formula, we're just adding in additional beta terms. So EY is still the DV score that is predicted based off the regression. Our A is still our constant or our intercept. And it's the predicted DV score when all of our IVs equal 0. Our beta is the amount the predicted DV score increases for a 1 unit increase in the IV, controlling for all other IVs. So we've said this a few times now. So if you're mathematically minded, I guess what that translates to is your beta is the expected DV score when your IV equals 1, minus the expected DV score when the IV equals 0, controlling for all the other IVs. So it's still the same thing, it's just removing the overlap. It's looking at just that unique variance. We can use our alpha and all of our betas to calculate the predicted DV score. So it's exactly the same as simple linear regression, we're just adding in these extra beta terms. So, let's see if I can do this. If I was to write up the regression equation now, what we would have is our expected ratings is going to equal, what's our intercept? Our intercept is negative 14.30 plus 3.45 for research plus 0.17 for building plus 6.70 for innovativeness. So it's exactly the same layout as last time, we're just adding in these extra beta terms, and it works in exactly the same way. So if I said that I wanted to predict the expected ratings of someone that puts in 1 hour of research and no hour of controlling, try that again, the expected ratings for someone who has 1 hour of research controlling for building and innovation, what I could do is go, okay, so expected ratings is negative 14.30 plus 3.451, and now to control for these, I simply put 0 in as their score, plus 6.700, and then that mathematically just removes them. Minus 14.30 plus 3.45. And that will give me my 1 unit, how much my expected ratings would be for 1 hour of research only. But I could do other things. I could say 1 hour of research, 10 hours of building, and 2 units of innovativeness, and then I could just multiply it out, plus 1.70 plus 13.40. And I could do the maths and come up with my expected rating score. So just like before, you can do anything you like with this equation. You need to be sensible, because otherwise you'll get silly results if you put silly numbers in. But you can do anything. The world is yours.